Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 26, 2025, exactly 1 week ago. It introduces a novel framework that reframes neural network pruning as a game-theoretic equilibrium, where sparsity isn't forced by a human rule, but emerges naturally from parameters competing for resources. The paper is titled, Pruning as a Game, Equilibrium-Driven Sparsification of Neural Networks. And as we'll see later, this method can reduce a model to less than 2% of its original size while maintaining high accuracy, which is really impressive. So, before diving into the results, Table 1 defines the different rules of the game tested by the researchers. The columns show the penalty weights, where beta controls the L2 regularization and gamma controls the L1 regularization. You can see configurations like extreme beta, which sets a high cost for participation to drive dominance. Then, the L1 plus L2 combined row mixes both penalties, and as we will see, this balanced approach helps the model find the most efficient equilibrium. Alright, having set the rules, these charts show the training dynamics. The top left panel tracks test accuracy, while the top right monitors sparsity. Notice the blue line. It maintains high accuracy, but as the sparsity chart shows, it stays flat at 0%. In contrast, the red line for the L1 plus L2 combined method takes a brief accuracy hit. Yet, it achieves near-perfect sparsity almost immediately, eventually recovering performance as the network finds a stable equilibrium. Well, while the plots visualize the journey, Table 2 lists the final destination for each configuration. Looking at the first row, very high beta yields the highest accuracy at roughly 97%, but notice the sparsity is 0%, meaning it kept every single neuron. In contrast, the bottom row, L1 plus L2 combined, strikes a much better balance. It achieves over 98% sparsity, keeping less than 2% of the neurons, yet still maintains a test accuracy of about 91.5%. So, digging deeper, these histograms reveal the actual distribution of participation scores for the neurons. In the top left, the very high beta model has values scattered to the right of the red threshold line, which means neurons remain active and result in zero sparsity. Contrast that with the L1-L2 combined plot in the bottom right. There, the distribution collapses into a single massive spike at 0, demonstrating how the game dynamics successfully force redundant components to drop out. Wrapping up, two takeaways stand out. First, sparsity works best when it emerges naturally from competition rather than being forced by heuristics. Second, this game-theoretic approach can remove over 98% of a network's bulk while preserving accuracy. It suggests that economic dynamics might be the key to efficient AI. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.